Well, hello everyone, and welcome to distributions. First, we're going to look at the normal distribution because it is literally the key to almost everything else that we do in statistics. So we'll begin with some data. Over here, you've got Bagel Street Deli and all their sales receipts for a week listed here. So let's calculate some values based on this data. First of all, the mean, which is called mu, since it's all the receipts. This is the population. And that's equal to the average of all these receipts. Then we have the variance, which is sigma squared, and that's VAR dot P, because it's the population, and then all the numbers. And finally, the standard deviation, which is standard deviation dot P, again, because it's the population, all the numbers. All right, so what are these numbers? So there's the mean. The standard deviation is the average distance from the mean of any of these values. So the mean's here at 10.36. So let's go ahead and record that right next to kind of the middle of the data. So we'll just put equals that value there. All right, now standard deviations are measured as average distance from the mean. So let's go one standard deviation down. So we'll take the mean and subtract off the value of the standard deviation. So 8.79. And as you can see, that falls right here at our color change. So in other words, all these values are within one standard deviation of the mean. And now between here and here is going to be two standard deviations. So let's see what the next value would be. Equals the mean minus, and this time it's minus 2 times the standard deviation. All right. Now, as you can see, we're also counting the number of values that fall in each bucket over here. So it looks like there are 34 values within one standard deviation of the mean. And then here, there's fewer. In this group, and then fewer still in this group. And this basically shows, and you'll see the pattern will become more pronounced as this reduces in size. These are sort of the extras. You'll see the pattern become even more pronounced. But basically, the rule that you should sort of keep in mind is that most values are close to the mean. That's why there's more here than down here. Let's go to the other side of the distribution. So that's equal to the mean minus one standard deviation. Oh, sorry, that should have been plus, my bad. And then over here is equal to the mean plus 2 standard deviations. All right. Now, as a result of doing all that, this built out as well. And now you can see the pattern more clearly. So you can see most observations within one standard deviation of the mean. And then you can see here 2 standard deviations, 3. Now, if we sort of did this pattern over and over and over again, eventually we'd get a smooth curve that looks like a normal distribution if we had enough values. And the reason the normal distribution is kind of cool is because it's got lots of great statistical properties. So let's look at just a few of them. So on a normal distribution, this is what's actually called a standard normal distribution on this axis here. The mean is set to 0, and then one standard deviation, which is also called a z-score. So 1z, 2z, 3z, and negative 1z, negative 2z, negative 3z. But I'm also showing here on the x-axis the raw score. In other words, the raw mean is about 10.36, and then we go up the value. It's about 1.5 of the standard deviation. So actually, it would be better to show this at one decimal place so that you can actually see that difference. Let me see if I can do that. There. So now you can actually see the decimal places. Okay. Now, on a normal distribution, it has certain properties. It's symmetrical and bell-shaped, so symmetrical, both sides of the mean. It does look like a bell. And the mean is equal to the median, which is equal to the mode, the center value. It's completely described by the mean and the standard deviation. So if you have those two values, you know exactly what this curve looks like. And the tails are what are called asymptotic, which means that they approach the x-axis, but they never quite touch, no matter how far out you go. So, which of the following is not a characteristic of the normal distribution? And that would be B, that it refers to sample data, because in this case we have population data. And we're all set. I'm ready to move on. All right, next we are going to test your ability to read these types of graphs. So fill out the table with the industry mean and the standard deviation for each graph, assuming that these graphs represent the industry mean for some industry. So in graph A, what's the mean? And here we're looking at the raw scale mean. It's going to be 90. And in the same graph, what's the standard deviation? Well, the standard deviation is as you go from 90 to the next value up, which is 95. So standard deviation is obviously 5 up. That's graph A. Graph B, the mean is 100. You can see here. And the standard deviation goes from 100 to 105, so that's again 5. Graph 3, the mean is 110. Oops. And the standard deviation is, again, 5. And in graph D, the mean is 120, and the standard deviation is, again, 5, 120 to 125. All right, so all of these graphs have exactly the same standard deviation, but they have different means. All right, the next one says what raw values are associated with these standard deviations. Sorry, that got cut off. You can always stretch it down. All right, in graph A, at plus 2 standard deviations. So at plus 2 standard deviations, so that would be from 90 to 95 to 100. So 100 at plus 2. And at minus 1, we'd go from 90 to 85. In graph B, at plus 2, we'd be at 122. And at minus 1, we'd be at 74. In graph C, at plus 2, we're at 110. And at minus 1, we're at 95. And in graph D, at plus 2, we're at 120. And at minus 1, we're at 90. All right, what are the values associated with these z-scores? Remember, z-scores is the same as the standard deviation, right? So the z-score of 2, that's effectively plus 2 standard deviations, so that's 122. maybe not. Oh, sorry, I was reading the wrong graph. So it's this one here. So it's 100. Z-score of -1 is 85. Z-score of 2 on B is 122. -1 on B is 74. On C, 110. And 95. And at D, it's 120 and 90. And if you've been paying close attention, you realize that all these numbers are exactly the same as these numbers. In other words, +2 standard deviations is a z-score of 2. -1 standard deviation is a z-score of -1. All right, moving on. Oh, wait, we still have some questions. Here we go. What z-score is associated with these values? So in graph A, raw value of 95 is a z-score of 1. In graph B, a raw value of 58 is here. That's a z-score of -2. Graph C, the z-score, raw value of 100 is associated with a z-score of 0 because it's the mean. And in graph D, a raw value of 130 is associated with a z-score of 3. Okay, now we're ready to move on. So get used to this. You've always got the raw scores, the z-scores, and this other axis that we're showing here, the sigma axis, is we're just showing, the actual +5, +10 that leads to these raw values increasing by the value of sigma, which is the value of 1z. Okay, back to our friend here. This was the same normal distribution. This time the value's been filled in for you. And we want to talk a little bit about a clever device called the empirical rule. So we're showing here on the x-axis certain percentages. And the way the empirical rule is phrased, it says, look, within 1 standard deviation either side of the mean, you should get 68% of all the values in a normal distribution. So if you divide 68 by 2, that means 34% are over here, 34% are over here. All right, within 2 standard deviations of the mean, so that would mean -2 to +2, you should get 95% of your values. So how can we get up to 95? So that's 68. The difference between 68 and 95 is 27. Divide 27 by 2, that means 13.5% sitting over here, 13.5% sitting over here. And within 3 standard deviations, you should have 99% of your values. So between 99 and 95 is 4 that's missing. So 4 divided by 2 is 2, so that means 2% over here, 2% over here. And if you take all of that, what's left is 1% to get to 100, so that's why we end up beyond 3 standard deviations with 0.5% over here and 0.5% over here. So if you memorize 68, 95, 99, you'll be able to basically on the back of a napkin create this distribution and write down the percentages and actually be able to answer questions like this. So what percentage of customers spend between $9 and $12? So there's 9 on the raw scale. There's 12 on the raw scale. And so it's going to be 34 plus 34, 68%. What's the probability of customers spending between 7 and 13? 7, 13. So that's going to be 95%. Percentage of bills are between 6 and 15. So that's way over here. So that's going to be the 99. What score is the mean, median, and mode? By definition, in a normal distribution, it's the one in the middle. So that's going to be a 10. What's the likelihood a randomly selected bill will be $10 or more? So that's half the distribution, so 50%. What bill is at the 16th percentile? So you add this way until you get to 16. So 0.5, 2.5 plus 13.5 is 16. Ends up being 9. And what percentage of bills are between 13 and 15? 2%. And what's the probability that a bill will be between 10 and 12? 34%. And what bill is at the 99.5 percentile? So that would be sitting right over here with the extra 0.5 missing. So that'd be 15. So you can use this as literally a way to very quickly, as long as you know the value of sigma and you know the mean, if you know the mean and the value of sigma, you could very quickly on the back of a napkin set this up and then write the, here's the mean, and then add, 1 sigma, 2 sigmas, 3 sigmas, and do this kind of thing. Well, this is great if the values fall right on the standard deviation, but what if they don't? What if they fall somewhere in between? This won't accurately give you the value. So we do need to know how to actually calculate precise values, because when we're doing hypothesis testing later on, we'll really need the precise values. And so the rest of this exercise is how you go about calculating those precise values on all these other sheets in the exercise.